Now, while the normal distribution is going to be the most important distribution for us in this course, the binomial distribution is another one that we do need to look at because it's going to help us when we're looking at inference for proportions. We'll start by defining a binomial experiment, and that is just a sequence of trials with the following four conditions. It has to be a fixed number of trials, so you have to know exactly how many trials that you're going to perform. Each trial can only result of one of two possible outcomes, and you'll label them success or failure. Now, success doesn't necessarily mean a positive good thing. It just means what you're looking for in the case of the probability experiment. The outcomes of different trials do have to be independent, and the probability of success is the same for each trial. If all of that is true, then you can create a binomial random variable x, where x represents the number of successes observed when the binomial experiment is performed. And so collectively, that probability distribution is called the binomial probability distribution. Now, example 6.5 was that long example with the 4 people buying the refrigerators. And we saw that it was a lot in order to get the 16 outcomes and then the probability of each of those 16 outcomes. Well, it turns out that that actually falls underneath a binomial experiment. So we could have just done this problem using the binomial distribution. So let's make this example a little bit tougher, one that we would not even consider doing by hand. If we have 5 customers, and this is actually going to be 32 different outcomes, and so absolutely not are we going to write all of this out. So here we need to determine what our success would be and what our failure would be. So we can consider the success to be getting an energy efficient, and then failure would be not getting an energy efficient refrigerator. So with that, if we want to start looking at some of the outcomes, we might have something like this: success, failure, success, success, failure. Or maybe success, success, failure, failure, success. Now, there are 30 more of these different outcomes, so we're not going to list them all out. But what we can do here is we can see that there was some pattern that was emerging when we were looking at these probabilities in section 6.2. What we're looking at is within the set of 5 trials, we want to count the number of successes. And it doesn't actually matter where the successes are, just the fact that there are that many of them. So in this case, if we wanted to do x equals 0, then we'd be looking for the case where it's all failures. And so the probability of each of those, the probability of failure was 0.6, and that's going to be to the 5th power. So we get a probability of 0.0776. Now what about getting 1? Okay, so that means that we are looking for exactly 1 success, maybe in the first customer, the second, the third, the fourth, or the 5th. And so we see that there's actually 5 possible places for that success to be. And then each of these is going to be 4 failures and 1 success for a total of 5 different arrangements. So we'll do 5 times 0.6 to the 4 times 0.4. So we're looking at 0.2592. Now, what about the 2? This one is definitely a little trickier because we're looking for 2 successes, and they can be in the first and the second, the first and the third, the second and the third. There's all sorts of different arrangements for that. So this is where we are getting into the actual formula for the binomial distribution. We have 5 possible customers, and we want to choose exactly 2 of them. So there's this process called combinations, and you would write it like this. It's kind of a parentheses, and it's 5 with 2. That means you have 5, and you need to choose 2. Out of your 5 possible locations, we want to pick 2 of them. And the way you calculate this nx, is going to be n factorial over x factorial n minus x factorial. Now, if you haven't done factorials before, it's just where you have multiplied the starting number and every number after it. So for this problem, if we have 5 choose 2, we're looking at 5 factorial over 2 factorial, 5 minus 2 factorial. The top, that's 5 times 4 times 3 times 2 times 1. And then 2 factorial is 2 times 1. And then 5 minus 2, that's 3. So 3 factorial will be 3 times 2 times 1. Now, you can get a little bit to cancel. You'll always have some that will cancel. And so here, the numerator is 20, the denominator is 2. So there are going to be 10 different ways for you to have exactly 2 successes in this particular this event that we're looking at. Now that we have that part, since there are 10 different possible arrangements, and for each of these you're going to have 3 failures and 2 successes, then we're going to take 10 and multiply by 0.6 to the 3 and multiply by 0.4 to the second power, and we get 0.3456. Now, I know your head is probably spinning because we've only done the case of 0, 1, and 2. We still have to think about 3 successes, 4 successes, and 5 successes. So I will go ahead and be upfront. You do not want to do binomial probability distributions by hand. There is a table, but I don't really like using the table either. I'm going to show it to you right now, but then there's going to be a separate video that's going to show you how to use StatCrunch for both the normal distribution and the binomial distribution.